So, good morning, ladies and gentlemen, to this day of joy, because it's the 30th birthday of the IBM PC, so that's what we're here for. No, actually not. So, we are going to talk about moonbounce communication, but not only moonbounce, but radio communication through space, through very long distances, and of course, to the moon. So, let's start. Yeah. Moonbounce is, of course, very simple. There is a very simple explanation for moonbounce. You have a radio signal, you transmit it towards the moon, you get a reflection back from the moon, which is just there hanging in the sky, and you try to receive that signal again, or maybe another station on the Earth. The first attempts to do this were done in the mid-1940s by the US Army Signal Corps. So, and what they wanted to achieve with that is, of course, to send a signal through the moon to another station on Earth without having to worry about all the weather, radio propagation conditions, and without the Russians listening in, which is, of course, not so easy because they can also see the moon. Yeah. Only a few years later, they invented a better way, which is just using satellites, telecommunication satellites for military, civilian use. So moonbounce was quite soon thereafter phased out for commercial use, but radio amateurs, only a few years after, started to do this as well. It's still done today. It's very demanding. It's really hard to do that in comparison to a lot of amateur radio things you can try, but it's of course fun. So this is what we do. Yeah, we of course start with some basics. A lot of you may know the basic radio stuff, but we have to do some groundwork. Everyone is on the same level. It's very, very easy. It's nothing complicated, so you will be able to understand it. Yeah, this is also radio communication, so don't worry. So, we'll come to that very soon. So this is just a quick overview of the radio frequency spectrum. You start, of course, with very low frequency over there, which is not so much interesting, except you want to communicate with a nuclear submarine underwater. But if you go to about this area, there is AM radio. Maybe you have switched your car radio to AM for a mistake and wondered what's there. It's about here. Very long wavelengths, low frequencies, and a couple hundred kilohertz. This is more. This is where amateur radios usually operate, shortwave frequency. There are also some shortwave radio stations. Not so interesting for moonbounce because the signal usually doesn't leave the Earth, so it stays within the ionosphere. Here it's more interesting, 100 megahertz. You might know that. This is where your FM radio works, so it's much more interesting, and also these signals can leave Earth and travel into space. For moonbounce, you use signals from here upwards. So we, as you can see later, will be in this area as well. Quite a bit farther up, below 1 gigahertz and above 1 gigahertz, you have GSM radio, which you just heard. So signals travel line of sight. You don't have any wide ranging communications there except with high power, and if there's no obstacle in between, which would mean through space. So you can do that. Communication satellites are in this area, 10 gigahertz. It's very good to reach the space through the atmosphere, which doesn't disturb it too much except when it's raining. Oh, yeah. And further up, there is nothing much more interesting. You would have the naked scanners in this area, which they want to set up on airports all around the world, and here's of course visible light. So this is just a quick overview, and remember we are working in more or less this. Here in the camp we're working this range, and this is actually the frequency range you use for moonbounce and satellite communications, so communications through space. Please, the next slide. It's still early, so just don't worry. We are sleepy as well. There is some. Yeah, okay. There is a second basic we have to know. This is the decibel. Decibel is a unit. Actually, it's a ratio unit, so it's nothing fixed. You can say this has 5 decibel. This is just a ratio that we need, and you will see why we need that for comparison. So just you have to remember 3 decibel means doubling of power, -3 means half the power, 10 decibels means 10 times the power, -10 means just a tenth of the power, 20 would be 100 times the power, that's it. The very good thing is, why we use that, because if you have very, very big ranges of power, you can just easily add them or subtract them. You don't have to multiply anything. There are not that big numbers involved. So this is where we like to use the decibel, and we will even have very, very simple example to show that. So if you want to have a set value, so not the comparative value, you use something like dBm. dBm is just a decibel compared to milliwatts. So 0 dBm would be 1 milliwatt of power. 3 dBm would be 2 milliwatts of power. 10 dBm would be 10 milliwatts of power. So it's quite easy to calculate. Next slide, please. Okay, so we want to reach the moon, as we said. It's quite far away. Actually, it's about 380,000 kilometers in average. It's a little bit closer or farther away sometimes of the year. So it's hard to reach it. You can see it, at least when it's up during the night, which is good. So you might be able to hit it with your radio signal, but it's still far away. So you have a lot of path loss. Actually, as I said, we use decibels. The path loss for moon signal to the signal path to the moon and back gives you about 250 decibels of loss. As you can see, -3 is half the power, -10 is the 10th of the power, so this is quite a very, very small number. Then there are different obstacles to communicate for communication with the moon. The signal you transmit is polarized, so you have a linear polarization, might have a circular polarization. Usually it travels to the ionosphere through the interplanetary space and back again, and it will get bent and it will get circulated. So you might not be able to hear a signal because it's circulated 90 degrees, which gives a lot of signal loss in receive. Nothing specific, but you have to know that. On the other hand, it's quite good if you're standing on the North Pole and another guy stands on the equator, you have 90 degrees polarization difference anyway, so that might help as well. And there is noise. So remember, we're talking about very, very low signals coming back. So every HF noise, like the power supply from your laptop, might really disturb that. So or a Tesla coil. Tesla coils are especially bad because they transmit on every frequency you can think of. Yeah, that's it. And the ionosphere, which is for our frequencies not a big problem, but you still have to remember that it's here. Next slide, please. Okay, as I promised, a very simple just calculation. We think about we have a signal of 100 watts, which is just like a standard light bulb, a bright one, the ones that are not available anymore in the European Union. So this would be equally to 50 dBm of signal power. Then we use, of course, a directional antenna. So you don't use an antenna that transmit all around with the same strength. So you use a directional antenna, which might give you a nice gain of 16 dB. The good thing is you can just add that to the 50 dBm, so you get 66 dBm. Then there's the path loss, and 250 dB is actually quite a good average. We are around here. Of course, antennas work in receive as well. We have another gain, which is, of course, nice. So we come up with a signal that is minus 168 dBm, which is this number in milliwatt. It are 17 zeros after the comma, so it's not very strong. Try to power LED with that, you won't get very far. So, yeah, that's really low power, but what can we do? Of course, we can just brute force it. We have more power. If we use 1000 watts instead of 100, we have 10 dBs more, only minus 176. So, hey, that's cool. Of course, we can have the structural attempt, which means you make big antennas with more gain. That's actually nice if you have a lot of space and a lot of money, because it's even more expensive than a strong power amplifier, but it's cool, of course. Radio dishes work nice if they are like 50 meters wide. It's great. And there is the smart attempt, just doing it intelligently. Sounds like it's me, but yeah. Like doing it intelligently. So use a clever communications protocol. What that means, I will explain in a second. But remember, the signals are so low that we do have to do all of that to be successful. Next slide, Peter. Next slide, please. Yeah. Okay. So how can we communicate via the moon? Remember, it's about sending a signal to the moon, reflecting it back and talk, or communicate with another station on Earth. So we don't want to talk to the moon because there's no one there. We can, of course, try to talk with people. That does work. You need a lot of power. You have a very wide signal, a couple kilohertz in width, so the bandwidth is quite wide. You need a strong signal, and as you might expect, if there is a lot of noise, you might not able to understand what the other guy or gal is talking about. So this is actually quite inefficient, but you can do it if you have the right equipment. Then you use digital modes. It's all about digital nowadays, but not only nowadays. Morse code from the 1860s is already digital mode, which you can do encode and decode by hand and with your brain, and this works much better. If you have a really good Morse code or a CW operator, you can hear more signals that are 12 decibels below the noise floor, and this is quite cool. I can't do that, but there are people who can. And there, of course, you have a computer, so it's much better. You can just type on your keyboard like you are in an IRC chat. Use some data transfer modes, like old things. This is just radio teletyping, packet networks, or this is where it's going to enter JT65. So this is actually the most advanced mode you can use for radio communication with the moon, and this is what we are going to do, and this is what we will explain to you and talk about. So there is an American physicist, Joe Taylor, K1JT, so who developed this JT65, but not only JT65, he's a really interesting guy, Nobel laureate in astrophysics. He is really one of the people who can just go to a receiver and say, hey, we want to use your big dish there to make moonbounce, and they will let him. So they did this last year, and with their setup, a 300-meter dish, you can really do voice communication. You can almost receive them with a handset like this. You just need a little bit bigger antenna, but this could be done. He wrote WSJT, Weak Signal Joe Taylor. It's a program suite, free, open source, available to every amateur radio and actually all people on Earth for weak signal digital communication. There are several digital modes in the program which you can use for whatever you want to do, but for moonbounce with JT65, and this is what we can. You can, with JT65, decode or hear signals that are even much lower below the noise floor than with Morse communication, around 25 dB or even better. So next slide, please. So this is the Arecibo radio telescope, which you can use for transmission as well if you like. So Joe Taylor did this last year. You don't have to use JT65, of course, for that. You can just talk and people will hear you, but JT65 is much more cool. So thanks, and now I will give the microphone to Clemens, who will just explain to you how JT65 works and why it is really cool. Yeah, are there any questions about the first stuff? We will have a Q&A later as well, but if you want to just have a question right now, we can answer that, of course. Okay, Clemens.
Okay, so the best thing you can do about modulation Okay, is this better? Okay, so the easiest thing you can do to create a modulation that's getting really fast is, increasing the power. So if you have got a signal here, and so this is the frequency, and this is the amplitude of the signal. And like this is your signal. It's very wideband, so you have a very low amplitude of the signal. So if you go to the next slide, this is a much better signal. There is not as many information in it as in the big signal, but the amplitude is much higher. And what we are actually doing is this. It's an extremely narrow signal, and the trick with it is that next slide. If you have a noise floor that's like this high or much higher, if your amplitude is high enough, you can still decode it. And yeah, that's exactly the same as JT65 is doing. So 65 is for 65 tones. It's frequency shift keying. And on 2 meters, we are using JT65B. 2 meters or 144 megahertz is the frequency we are transmitting and receiving. And it's one tone at a time with a continuous amplitude. That makes it easier for power amplifier designing and receiving. So you have got a constant tone that's only changing in the frequency. The bandwidth of the signal, the maximum bandwidth of the signal is 355 hertz, and the tone spacing is 5.4 hertz. So the tones are really, really narrow. And every half time there's a pilot tone. So there's another thing. What JT65 is doing is it is a massive forward error correction. It's a Reed-Solomon coder, and it can decode up to minus 27 decibels under the noise level. If you have got something like wireless networks, you need about 20 dBs above the noise level to have a good signal. So that's really, really good. So we are transmitting time synchronous, so you are sending like 47 seconds, and then there are 13 seconds left for decoding and user interaction with the program. And the other minute, the other station is transmitting, and you are receiving. So there, you can say it's one packet is about 1 minute round trip time. And you're actually doing this with prepared text messages that are really small, and there's not much information in it. So we have got a few sound examples. We will at first transmit a signal that's 10 decibels above the noise level. So you can clearly hear the tones. There's a signal that's exactly on the noise level, so 0 decibels above the noise level. Oh, okay. Sorry, that was the wrong file.
This is not what we heard from the moon.
So this is already a bit harder to understand. So the next file is 10 decibels under the noise level. So you can guess the tones, but it's not really decodable by your ear. And the next sound file is 20 decibels under the noise level. Yeah, so you can't hear anything, but with a computer and the demodulation signal, it's very easy to decode it. So next slide, please. Yeah, that's a standard QSO. On the left side, we've got our station. That's Oscar Echo 5 X-ray Mike Lima, or call sign, amateur radio call sign. And we have got the CQ on the left side that we are looking for a station to answer. Then we are of course communicating with K1 JT. So he's answering that he heard us with his call sign. And so we are transmitting that we heard him with our call sign and that we decoded his message. And that's just 000, so the signal is okay. The next thing K1JT would transmit is RO, like Roger. And the last thing you need to end an Earth-on-Earth communication is the Roger, Roger, Roger on the end. Normally, you're also transmitting 73. That's like greetings to the other station. So that would be a standard QSO over the moon. And if we had success, we will see in the delay, because it's also possible that we can receive the signal over the ionosphere from objects, but there's only one option left when you have got about 2.5 seconds delay of the signal, and that's the moon and back. So, for example, the distance Berlin-Paris is about 3 of 1,000 seconds transmit time, so it's really a long round-trip time to the moon and back. You can also do pings to the moon. That's like you're sending a short signal and trying to receive it with your station, and you can hear echoes from the moon. So about our setup, we are using 2 stacked Yagi antennas with 10 elements. They are about 6 meters long each. And we are using linear polarization, and they have got together 16 dBi gain, so it's 16 dB over a perfect isotropic radiator. You don't, for decoding the signal, you need, of course, transceiver, but also a very good low noise amplifier. We have got a low noise amplifier from Kuhne. That's a German company that is producing really good super low noise amplifier with over 28 decibels gain and about 0.3 decibels of internal noise, so that's really good. For transmitting, we have got a linear power amplifier with about 750 watts. That's the maximum. We are legally allowed to transmit, so it's quite good, but it's not enough if you want to do Morse code over the moon. You need about 4 times of that power to get Morse code over the moon, to transmit and receive it. For transmitting and receiving, we have got a really thick cable that's 1/2 inch. That's used for GSM stations. And so it's super low noise, super low loss cable with about 0.2 decibels per meter at 6 gigahertz, which is really, really good. And as I already said, they are using it in GSM stations. They are also using thicker cables, but that's the normal cable when you're going to a small or medium-sized antenna. And we're using a high-power coaxial relay between the power amplifier and the low noise amplifier, because the low noise amplifier is very sensitive to incoming power. So if you have got a bad coaxial relay, you are just burning your low noise amplifier, and that was your moonbounce action. So that's our setup. We've got the mast here, the 2 antennas. They are combined over a power combiner, and here's the coaxial relay, whereas the low noise amplifier is directly connected to a coaxial relay, and then we are going with the thick cable to the power amplifier and a small transmit or receive coaxial relay that's just switching the receive and transmit path. Yeah, that's our setup this morning. We have not fully finished it. I hope, or we hope, it will work in the evening or in the night. And yeah, mechanical things are already mostly done. Just a few cables. We have to run just a few cables, and yeah, measure the antennas if everything is correct. So that was my part. Are there any questions? Okay.
So the moon is at these days only up in the evening, so it rises at like 9 in the evening and sets like 5 or 6 in the evening, in the morning. So you say, what should we do in the rest of the time? That's something very nice we can do. We can talk to amateur radio satellites, or we can listen to any kind of satellites, but in fact, we like to listen to amateur radio satellites. Just for comparison, 1957, the first satellite was launched, Sputnik, and in 1961, already the first amateur radio satellite, the first non-government, non-commercial satellite, as far as I know, was launched. It was since then, more than 70 amateur radio satellites have been launched and are still working. The longest working satellite now is 35 years in service. It was kind of busted in between, but recently it started working again. So you see, it's no matter of high tech or something like that, it's things that work. These satellites are completely funded, built, and operated by the amateur radio community. And as you see on the number, it's now by 12th of December, it's 50 years that this is happening all the time. So I think that's quite something. Just for the relations, if you have here the Earth, low Earth orbits are from 300 kilometers to up to 2,000 kilometers. The ISS is now at about 380 kilometers. The Hubble Space Telescope is about 570 kilometers. That's the area where most of the amateur radio satellites are, and which is easy to reach because you don't need so much energy to get up. GPS is much higher at about 26 kilometers. Geostationary satellites like TV satellites, Astra, here in Germany and Austria is very popular. They are at 36,000 kilometers. So you might now ask, and where's the moon? So this distance is 36,000 kilometers. The moon is 380,000 kilometers away. So look like 20 meters in this direction, and you have the moon. And it's in the size of like 2 hands. So you get the relation of what we were talking before. So working satellites is much easier. Next step. In fact, you don't need very much equipment. You can use something like Momo amateur radio handheld and home-built antenna. I built this myself, and it was not very difficult. But you can even use a good dipole antenna with your handheld. Of course, you can do with more power, more money, and you can have a station transceiver, low noise amplifier as we had before to get stronger signals. You can put your antenna on a rotor and turn your antenna from your warm home, not to get out in the winter or something like that. But very important, you don't need much power. It's not the thing like you have to blow down this satellite. In fact, they are not very happy with high power because they have low power. They have just some watts. Some satellites even work with milliwatts of power. So if you put a strong signal up, the satellite has to respond to this signal with a strong signal, which takes a lot of power, which is not favorable. Next one. Okay, what can you do with a satellite? You can do almost all modes, from terrestrial communication. You can do CW. In fact, most of the satellites send beacons where they transmit their current state, like, okay, I'm a little bit hungry, give me more sun, or I feel a little bit cold, or I feel a little bit hot, or I'm in a very happy state, or I'm in an emergency state. And of course, you can also do QSO over it. That's the amateur radio term for a communication. You can do single sideband. That's an amplitude modulation scheme, which is more energy efficient. You can do frequency modulation, which is the same on your radio. You can do all kinds of digital modes, like phase shift keying, which is very narrowband. All other kind of digital modes. You can do packet radio, which is kind of like modem communication over. Wat nog? Geht's noch? Klik nou maar op die folie. Okay.
Just a minor technical problems.
Was ist denn die nächste Folie? Not working anymore, sorry. Kannst du das irgendwie zum Laufen kriegen? And there are other new modes, like last week a satellite was launched out of the International Space Station. They just throw it out of the window, something like that, and it has interesting new ways to receive. You can even receive it with a handheld radio and still code it. Next one. Okay, how do you know where to find the satellite? These satellites are moving rather fast. They rise and set within 10 minutes, something like that. So you have to know where to point your antenna. There's lots of software on the internet for Windows, Mac, and of course for Linux. I prefer open source software, and my favorite is gpredict by Alexandru Sete. He's a physicist in Denmark, and he's a very nice maintainer of this software. I already contributed a little bit, and it was no pain. Yeah. So you see all the satellites. You see the path they are traveling. It's a little bit hard to see, but for example, here you see one of the famous amateur radio satellites. You see, where's the ISS? There's to be the ISS somewhere. Anyway, and here you see the point where we are located. Now that's my hometown, and the area which the satellite would cover. So if you are here at that spot and work over this satellite, you could reach as a person like in this area. And I think that's quite something. Yeah, that's quite a range. Umschalten auf gpredict. Maybe we can show you a demonstration. Never mind. We do it afterwards. So you get here this diagram, and you can look at where in the sky is the satellite now, and I just point my antenna in this direction. That's quite forward. Okay, next one. So if you want to see how this is working, here in the shelter it's a little bit hard. You can visit us. The moonbounce thing is at the Leibandville over there. It's next to Baikonur with the red pylon. You see it most in the night. But you just look up where the big antennas are and ask for the moonbounce people, and you find us. The satellite people are next to them with the blue board. And maybe you see us sometime in the evening standing on the street with some weird things and with dangerous rods, and asking you to step back a little bit. That's the satellite people. And if you want to know how such a satellite could be built, there's a lecture in the evening about Moorsat, which I'm working on in this project, and it's about building one of these amateur radio satellites, in fact. So if you're interested, attend the lecture. It's at 7 p.m., I think. Okay. One thing we did not have on the slides is all three of us were licensed not more than 2 years ago. We are quite new in the amateur radio thing, and we were interested in because we want to do this radio stuff and how to do it, how to get a legal possibility for something like this, and we decided to make the exam, and we are now doing this stuff. It's not hard. You can do it yourself if you think it's interesting. So just try it. It's no big deal. There are a lot of nice people helping you, and amateur radio people are generally quite nice and relaxed. Yeah. Okay. So hope it was interesting for you. Are there any questions? Yeah? Someone? Would you like to come? Pardon? Yeah, the link budget? Yeah, the link budget, yeah. Which is left over? You end up with, I didn't get the question. You end up with something like, this lecture is recorded and, yeah? Mike? How many dB?
He's asking about the link budget for EME.
For
Hello?
EME.
Okay.
We had this link budget. You end up with something like 70 zeros. It didn't get the question. Anyway, you end up with something like -20 to -27 dBs. That's how it's working. Yeah. Other questions? Yeah. The microphone.
Word.
For satellites.
Yeah.
There are some satellites who do digital communication, and you can get up to 9,600 bits per second. That's not very much, but it's quite something for a do-it-yourself thing. And to the moon, it's much less. I think you have like 5 bits per second, something in that range. It's just like a big distance. There's a question over there.
In the amateur radio range, can we expect to extend this data rate? And the second question is it possible to do a ground station by myself? Can I make my ground station without buying anything from start companies?
Can you tell me again? I didn't hear it from the monitors. No.
So there is 2 questions. The first one is, can we expect to extend the data rate with satellites? Because in order to make a new system of communication, I think that we need to extend the data rate.
Okay.
And the second question is, in order to build a system, a ground station, is it possible to build the ground station by myself? Or do I need to buy something from standard companies, or is it possible to homebrew everything?
Okay, the first question is increase the rate. It's very hard. You have seen we are very limited, and it's hardly working. Okay, so increasing the data rate above the moon is very hard thing to do. You can do it. You can put more power on it. You can put more antennas. There are people who have like 30-meter wide antenna arrays, and they have a lot of antenna gain, and they have big power amplifiers. You can do it. But moonbounce is nothing like, okay, it's the new replacement of GSM radio or something like that. It's more a proof of concept and a hobby than efficient data transmission scheme. The other thing is, you can get something like this transceiver, handheld transceiver, from something like there's a Chinese copy of a known type, and it's about 35 euros. You can build something like this antenna with a budget of like 50 euros. So it's no big deal. Of course, you can throw more money on it, and if you buy something like this power amplifiers or this low noise amplifiers and all this HF stuff, of course you have to spend some money on it. But on the other side, you also spend some money on your keyboard or on your computer or on your monitor. So just depends on where your priority is. But it's completely affordable. We all do it, and we are not poor. Yeah? Or we don't get poor out of it. That's what I wanted to say. Okay? One more question? Or is the time up?
I'm here for questions. I'm sorry.
Yeah, okay, we have some time. Yeah?
I have one question. Does it work? There's one question from the audio angel, and he asked if you can reach satellites with low power handhelds, is it possible to do a DOS attack against satellites?
I didn't get the last thing. Is it possible to?
Is it possible to do a denial of service attack against satellites?
Okay. I know, sorry about this. It's like in the beginning of the 1990s, there were people trying to hijack television satellites. And they succeeded. They just put a big dish somewhere in a country where you are not prosecuted for, or very fast prosecuted for things like that. And they pointed this dish to a satellite, to a television satellite. And for some minutes, they were able to be stronger than the original signal of the uplink station. That's something that's very hard to mitigate on satellites. You have a shared medium, and in a shared medium, you have to cope. There's no enforcement of it. Amateur radio satellites can, of course, be denied of service, but what's the point? So who's interested in jamming something that's for hobbyists? If you want to do it with some professional communication satellite, okay, maybe you have some agenda or something behind. But yeah, it's possible. Can't do very much about it. What they did with the television satellite, they found out that they were jammed. They turned up the volume or the power, and the thing was over. Yeah, it's just like that. The stronger one wins, and yeah, that's the thing.
My question is about ground networks. You said that you're using the handhelds and Yagi antennas. But some persons you might know from the other side of the Atlantic, they are interested in acquiring old, abandoned military dishes because they make a much better station for moonbounce. So I'm wondering how the acquiring old, abandoned dishes situation looks like in this side of Atlantic.
It was very hard to understand.
Old, abandoned dishes. Can you reuse them, I think, was the question.
This is already, they're already in use from on the other side of the Atlantic, that is in the USA. So I'm just wondering, is there similar activities in the European side as well to acquire old, abandoned military dishes to communicate with satellites?
There is surplus equipment you can get even here in Europe. It's no.
These are like the dish stations, the complete dish station that was built to communicate with military satellites, but they abandoned it when the Soviets went back from the eastern part of Europe.
I don't understand it because the sound is going in front. Just say it again to me.
When the Soviets left the Eastern Europe, they left many of their military bases.
Okay.
These military bases are like really completely furnished with their dishes.
Okay.
The same things are taken in the United States for moonbounce.
Okay. I don't know, but what I know is in Bochum, there's an amateur radio station It was a scientific amateur radio station. It's a 20-meter dish, and it was abandoned, and they took it over. Now it's a museum, and people are very happy that they care for it, and it's a great thing. They want to use this as antenna for a Mars mission, a satellite that goes to Mars. So, and they also had a proof of concept. They sent a ping to Venus and got it back again. So, yeah. Maybe you find some of these old Russian stations, and maybe you can bring someone to sell it to you. I don't know. Have not heard about it, but maybe, yeah.
It's a good example of using the existing military technology for civilian use, so that's something I'm interested in.
Be creative, do it. It should do the job. Okay, one more question.
I don't know if this is true in Europe, but in the United States, it used to be very common for people to have very large television antennas for satellite television, like C-band, 4 gigahertz. This is no longer very widespread. At least in the United States, everyone's using digital television on little tiny dishes. I wonder if there's any extra capacity on these old television satellites, or are they being used for other things? Is there a possibility to reuse some of the old C-band equipment for internet or other data communications?
Okay. There are 2 parts of the antenna. The one is the dish and the thing to turn it. Okay. And the other one is the feed, where you actually get the waves into the cable. So you can change the feed, and the dish is still the same. It's just a parabolic surface. So you can change the feed, and you have a completely working dish.
I'm sorry. The question I have is the satellites.
Okay.
Are the existing satellites for 3-4 gigahertz television, can they be reused? Because there's a lot of satellites which are probably quite old from the 1980s that may have capacity. Is there a possibility of reusing existing commercial satellites which maybe are not being fully utilized anymore?
Okay.
Are you aware of any?
I'm not aware of it. What I can tell you is that geostationary satellites usually run out of fuel and cannot be reliably controlled. That's why they have to be put out of service. So if you find a satellite with enough fuel to control it and to remove it afterwards, that's also very important. Maybe you can use something like this. I've heard of a satellite project where a communication satellite, which kind of makes GSM via satellite, was built and was put up into space, and the company went bankrupt. There was an initiative to raise money to buy this satellite and to move it somewhere over a development country to provide service there. Something like that could be feasible. Yeah. But I'm not aware of something like this. It's an interesting idea. Yeah. But I can't say more than this. Okay. Yeah. I think there are no more questions.
I think there are no more questions now. Questions? Okay.